triệu chứng của dạ dày không còn nữa. Mình đã có thể ăn được tất cả mọi thứ, không phải kiêng khem bất cứ thứ gì như ngày trước.
Trào ngược đến giờ cũng không thấy bị tái lại nữa.
Tôi dùng 5 ngày thì hết trào ngược rồi. Ăn uống, bụng dạ thoải mái hơn nhiều lắm. Ăn ngon, cổ họng hết đau. Tôi rất là mừng. Vâng, thưa quý vị và các bạn, đó là chia sẻ của một người bị trào ngược dạ dày nhiều năm, đã điều trị nhiều nơi mà chưa khỏi. Người đã dành cả đời nghiên cứu về bệnh dạ dày, với một số thành phần đặc biệt mà thầy đã cất công nhiều năm nghiên cứu ra. Thực hư như thế nào? Chúng ta sẽ cùng tìm hiểu ngay sau đây nhé.
Tôi, bác sĩ Nguyễn Văn Toại, hỗ trợ bà con về tình trạng dạ dày không cần nội soi, chỉ cần 2 gói bình vị quản mỗi ngày, viêm loét hay trào ngược đều ổn định tại nhà. Để lại số điện thoại để được tôi tư vấn, trực tiếp làm rõ tình trạng dạ dày lâu năm. Tôi khẳng định với bà con sẽ ổn định hoàn toàn tình trạng dạ dày. Với bình vị quản đã được tôi nghiên cứu trong vòng 6 năm, tôi sẽ đồng hành với bà con giúp ổn định, không lo tái phát. Ngày hôm nay tại đây, tất cả những ai đang bị trào ngược, viêm xung huyết, loét hạng vị, tá tràng HP, sau 3 đến 5 ngày ổn định toàn bộ hệ thống tiêu hóa, đầy hơi khó tiêu, đi ngoài. Sau 7 đến 10 ngày ổn định nóng rát, tức vùng thượng vị. Sau 15 ngày đến 20 ngày ổn định về trào ngược. Tất cả những bệnh nhân cũ của tôi đã đặt niềm tin sử dụng bình vị quản và đã ổn định tình trạng đau dạ dày.
Hiện nay mình đã có thể sinh hoạt như bình thường, ăn uống thoải mái. Rượu bia thì thỉnh thoảng uống cũng không thấy đau dạ dày nữa. Mình cũng đã quay trở lại với công việc văn phòng và tiếp khách như trước kia. Mình cảm thấy là mình cũng rất may mắn khi có cơ duyên biết đến cái bình vị quản này. Đến giờ này nhớ lại quãng thời gian trước kia, mình cảm thấy rất là sợ. Cảm ơn bình vị quản rất nhiều.
Đau tức phần bụng này, cái phần thượng vị ấy, thì cũng không còn nữa rồi. Các triệu chứng đau, nóng rát này, khó thở này, nghẹn này là không còn nữa.
Sau một thời gian sử dụng ấy, thì tôi thấy bệnh dạ dày của tôi nó đã thuyên giảm rất là nhiều và gần như là khỏi hoàn toàn. Tôi cảm thấy rất là vui mừng được bình vị quản chữa trị, và tôi cảm thấy là đây là một cái giải pháp rất là hiệu quả. Cảm ơn các bác sĩ Toại, bình vị quản và đội ngũ hỗ trợ rất nhiều.
Xin được vinh danh công ty trách nhiệm hữu hạn dịch vụ BC, phòng khám cổ truyền Phúc Thành với hơn 30 năm hoạt động tại Hà Nội. Sản phẩm dạ dày bình vị quản trải qua 6 năm nghiên cứu từ năm 1997 đến năm 2003 và phát triển bài thuốc trong 20 năm từ năm 2003 đến năm 2023 của Phó Giáo sư Tiến sĩ Nguyễn Văn Toại.
Side. Let me show you what I can do. Obviously, it's oscillating and can take different size drums and the belt for sanding inner and outer contours. But what's always been bugging me with these machines is the drums and belts are this tall and most workpieces are not, resulting in only using the lower part of the sanding grid. Sure, the drums I can just flip around, but the belt is directional. Flipping it around, you could catch the seam and rip it apart. So a key feature of my sander is a height preset. I can lower the whole mechanism down and use the upper part of the belt. Isn't that fantastic? It also works super smooth. Changing belts is done easily by flipping a lever, and the whole belt attachment comes off with this lever. Sweet! One feature I decided against is a tilting table. That's just inconvenient. On my machine, the belt tilts. Much more useful. It's effortless with this lever and clamped with a single knob. There's nothing on the other side, everything done from here, but it gets clamped on both sides. I'll show you later how that works. And the big dust collection port is out of the way in the back. That's everything from the outside. You will never believe how I made the oscillation mechanism inside. But first, let me tell you the stupid reason why I built this machine. Not because of the mechanism. A few years ago, I bought this sander with way too many sanding belts now sitting in storage. And I just wanted a better use for them. Really stupid, but that's the truth. Now, how do you approach such a project from scratch? Where to start? Well, I'll try to summarize. I wrote down a list of requirements with features I wanted the machine to have, like the tilting belt, the height preset, and so on. Then when designing at the computer, I put each feature into its own assembly. So this does the oscillation, This does the tilting, you get the idea. And wherever possible, I try to integrate multiple features into a single assembly. Sounds straightforward, but all that was the hardest part. I spent a lot of time designing. But then you can build assembly after assembly and bring them together. So let's get back in time when this didn't exist and begin with the oscillation mechanism. I've got this precision ground shaft which needs to move up and down together with the sanding drum. A common solution is a geared motor with a crank. But to me, that's kind of boring. I wanted to couple the mechanism mechanically to the spinning shaft with a gear reduction. That should be interesting. From my machine specs, I need a gear reduction of 25:1, and I could do that with a worm gear drive. Every turn, the worm advances the gear by 1 tooth. It has 25 teeth, and I've got the right gear reduction. And then I can slide this into this housing, add a crank pin here, and there's the complete oscillation concept. It's a great concept with few parts, but 3D printed like this, it can't survive long term. This has to be metal and constantly lubricated, so I would need to find just the right one off the shelf or have it custom manufactured. That's not gonna happen. So another mechanism with a high gear reduction is a cycloidal drive. And if you ask yourself what that is, take a look at my logo. That's a cycloidal drive. Conceptually, it's simple. We have a housing with pins, the shaft with an eccentric cam, the cycloidal disc, and an output ring. The shaft goes in the housing with the cycloidal disc on top, and when I spin it, it does this kind of motion. The output ring fits on top and turns that wobbly motion again into a smooth rotation. The gear reduction is the amount of teeth of the cycloidal disc, so in this case 9:1. This concept I'm sure I can make reliably lasting with simple off-the-shelf parts and 3D prints. And so now we've got a fast spinning shaft and a slow spinning gearbox, but no oscillation yet. On this concept, the output gear is oriented 90 degrees to the main shaft, making the crank possible. And I still need that for this one. Bevel gears, for example, could do that. But again, I don't see them lasting a long time. So what else could create oscillating motion? Let's start simple with this ramp shape. If I move this back and forth, you can see the intersection here is moving up and down. And I could pick that up with a bearing. Now let's mirror that ramp, and the result is one up and down motion without changing directions, or rather, one full oscillation. But how is this helpful? Well, when I wrap it around a cylinder and make it spin, I now get continuous oscillation. And what actually matters, this cylinder is the same orientation as my gearbox output and a single part. No need for bevel gears. So I think we have quite an elegant solution here and can get serious making the real version. Getting serious means a lot of 3D CAD work. I modeled the entire assembly with every component before I ordered parts or started printing. But here we go. There are many printed parts, a few bearings, pins and screws, and machine parts, which I need right now, so I cut off pieces from some tubing. The longer bushing goes on first, with a washer and screw as an end stop that I have to play with, of course. Let's put that aside for now. Now the gearbox housing. The pins this uses are actual steel pins that fit in these holes that I still need to ream. The automatic compressed air comes in real handy here, removing the chips. The underside then gets a bunch of nuts pressed in, as well as a few on the inside. I could have also used the CNC Kitchen melt-in threaded inserts, but what they don't have is a plastic lock ring, and since I'm expecting vibrations, I wanted that. This bearing is a light press fit in the center, and this ring goes on top, clamping it down, making this my fixed bearing. The large bearing fits around the housing, where it first slips down easily, and the last little bit is again a light press fit. And then insert all the pins. Next, I need to make sure the cycloidal disc is sized correctly and moves freely in the housing. So when I put it in place, it should just drop down. But it doesn't, and I have to press it down. It does move, but it's pretty tough. I kind of expected this here, because I designed and printed this with no air gap, and when that's a real mechanical part, it's basically guaranteed to bind in some way. I need some amount of air gap in here, but just don't know how much exactly, so let's find out. I printed 5 discs with increasing play for testing, starting with 0.05. And it already drops down,
but the movement is still kind of rough. 0.1. Yeah, that's a bit better, but there's still some places where it feels like it's binding. 0.15. Yeah, now it's getting better. 0.2. Yeah, that's great. And 0.3 is probably no improvement, just more play. Here you can see the play. This is 0.05 and this is 0.3. 0.2 seemed to be the sweet spot. Let's go with that.
A bearing gets pressed in, followed by steel bushings in all the holes, which came in an interesting packaging. And then a second one. But before the discs came another ring first. It has some holes to ream, nuts to press in, a center bearing, and then the output pins, because this is part of the gearbox output and it sits below the cycloidal discs. Now the parts can come together on the shaft. First the housing, then one of the spacers, and the output ring.
Next come the eccentric bushings that create the wobbly motion.
Their center hole needs to be reamed as well.
Then I have a feature in them which positions them opposite to each other like so. To fasten them on the shaft, there's a pocket for a little square nut and a tiny set screw. And now the disc. Wait. Oh crap. I forgot to file flats on the shaft.
And disassembly is not as straightforward.
Yeah, at least I didn't forget to mark where to put the flats now.
Since the steel is hardened, I'm using a diamond file and it bites into the material well. But there has to be a more accurate way of doing this. I put two square blocks at the ends and this piece which holds the file parallel and at the right height. No need worrying about steady hands. But the real benefit is the second side, because I just need to flip the shaft and the second flat will be at a perfect 180 degrees to the first. Simple technique, but great results. The other flats are for later. Now I'm much more confident in the set screw and the cycloidal disc can go on top. I was really keen on testing, so let's do it.
This looks nice.
So now the second disc.
I need two discs because having only one wobbling around would vibrate. So having a second one opposite to the first one, the vibrations will cancel each other out. But I have to make sure the second disc is oriented correctly to the first one in the housing. Otherwise these output holes won't line up with each other. Since I have 12 output holes and 25 teeth, this is not symmetrical and there's only one correct position. So I put a little notch at one of the holes to make this simple. Right here. Looking straight down, you can now see how the holes of both discs kind of do a circular motion around where the output pins will be.
So let's put them in.
That looks promising. The remaining 3 holes are for screws.
And after reaming the pinholes in the lid, it goes on.
On top now goes the actual gearbox output with matching holes, and on the outside there is the integrated ramp, which I made a lot smoother, and it also fits a bearing.
As usual by now, reaming the holes and pressing in a bearing, then the last spacer washer, and then assembling all the parts together. The screws hold everything together, but I have to tighten them by feeling, and this is my by feeling phase. Without context, this looks really stupid. And finally, a dust cover with an improvised labyrinth seal.
Oh yeah, that's the gearbox done. What a nice little compact unit, basically full enclosed and protected from dust, which is nice. It's super smooth. I can't really feel resistance other than the 6 fresh bearings. And what you might not expect is this is back drivable, which means it works when I spin it here or here. That's cool. Just too bad you can't really see the inside now working. Let's fix that. There you go, I cut it open. Let's see it in action.
So for this short sequence I had to disassemble everything again, but this then at least allowed me to add grease when reassembling.
But still, can this survive long term? Because it will run a lot. Well, I'm confident because all the motion is either done by bearings, metal on metal, or at least well lubricated plastic on metal contact. And even if that's still not enough, I've got one more trick up my sleeve. Because thanks to the sponsor of this video, JLC 3DP, I've got all gearbox parts and some more for later printed from nylon, a much tougher and more suited material than PLA.
Other manufacturers also know that. For example, this gear in my planer gearbox is also made from nylon. While we're in here, let's clean it.
And look at the print quality. That's just nice.
Much better than what I could achieve. And ordering these parts from JLC is pretty simple. If I print them myself, I export the 3D model and import it into my slicer software. For the order, I just upload the same file to JLC 3DP. Here I could then choose the 3D printing technology, in my case SLS with nylon, the amount, and I instantly get a quote.
For example, 2 cycloidal discs are just $6.50.
Just like my own parts, all these of course also need some reaming before assembly, but then they pretty much go together the exact same way.
And there it works. Nice. The heart of my machine. If you need custom parts, give JLC 3DP a try. Their printing service starts at 30 cents. Their CNC machining service starts at $8. And if you use my link in the description, you can get a $60 coupon. But for now, let's disassemble it again, because until the final assembly, I want to stick with my parts, because I of course want to see if they work. The next part that goes on the shaft is the pulley.
It's made from the pulley and the pulley support and starts out as this chunk of aluminum. This first gets a facing cut and then turned to size with a few roughing and finishing passes and a chamfer. It's a non-critical dimension, but still nice when you hit the 45mm exactly. I used a 3D printed template for transferring the hole locations and then cut the piece off, but forgot to record. It could have looked like this. Except the diameter is too large for my tools, so the last bit is for the hacksaw. A quick jack jaw swap to clean up the second face, and then heading to the drill press for the threaded holes. Spot drilling, chamfering and threading. Standard procedure. For the set screw hole I installed 2 screws that position the piece correctly in the vise, and with the ruler method I made sure the part is centered. Then I carefully spot face with an end mill and do the rest. For now, this piece is done. The pulley starts as a scrap of polyethylene sheet, which I placed on the CNC router to cut the screw holes and a slightly oversized circle. Cut out, it goes in the chuck where I marked the rough size of a pocket, which I turned to a snug fit with the pulley support, followed by chamfers and removing this material, which creates very fluffy shavings. Then the pulley support goes back in the chuck where I faced it one more time and then screwed on the pulley with a dab of Loctite on the bolts. I turned the diameter to size and sharpied it black to better see what comes next. Finding the edge with the tool, move it to the center, scratch the surface and zero the dial. Then plunging to a certain depth, creating the V grooves for the belt and breaking the sharp edges. The last feature is a precise center hole, which I drilled and then carefully turned to size. It took many passes, but I hit my target and the result is this.
Ah, perfect. Alright, next comes the upper bearing block.
The upper bearing sees more of the load when I'm pushing against the sanding drum, so I made the bearing housing from aluminum. Here I marked the side centers, which helped me to position the piece at the correct location on the machine bed. There, I first machined the holes that align with my hole grid, so I can use 2 bolts to hold it down, and then I let the machine go to work. The finishing pass is really satisfying, as well as the chamfer. Turned out really well, but right now the bearing doesn't fit, because the CNC is not accurate enough for a bearing seat. And I want to turn that, so somehow I need to hold it on the lathe. I've got some round offcuts from a laser, that should work. I marked the center and the whole spacing of the two hold-down holes, which I then quickly turned into threads. With a magnet on each jaw, the plate has just a little bit of stick out. I face it by leaving some material at the center, and after about 1 mm, I turn it to a nice fit with the aluminum. That puts it in the perfect center, and I can hold it again with bolts. I left myself about 1 mm of material so I can do multiple passes and get it accurate. And I think that paid off. The result is spot on. Then turning the hole to final depth. At the drill press, I drilled and tapped the outer holes to M6 and the inner holes to M3. But since they are blind holes, I finished the threads with a drill and a low clutch setting.
The bearing nose should be a light press fit. And it's not. Oh, fuck.
Turns out the bearing is also slightly undersized, which I should have measured before, but at least I can now try out a trick my dad told me. A layer of Sharpie. It's a few microns thick and should solve the problem.
Oh yeah. That's a press fit now. Nice.
And the 6 screws hold it in place.
The last part that goes on the shaft is the drive block thingy that engages with the sanding drums.
It's straightforward and similar to the pulley support. I face and turn some stock to size so it again fits the template, chamfer it and cut it off. This time with recording it. Flipped around, I face it to length and then drilled and turned the hole to the same fit as the pulley. Then transferring the hole positions, drill and ream them to size and depth, and hammer in some pins, which will engage with the sanding drums. They also line the part in the vise for the M6 set screw hole.
Very nice. Everything is mounted, but it's far from being a finished sander. This needs to be mounted in something, and I call that the sled.
The sled basically is a wooden box where all parts have different features cut into them, and after a bunch of toolpath programming and flattening the CNC bed, I can begin. The workhorses are these single flute bits in different diameters. They allow me to take aggressive cuts and remove a lot of material. But first I have to prepare my material. Some 18 mm thick birch plywood, which I cut into roughly oversized pieces, and then cut a shallow groove all around for my hold-down clamps. This gives me access to the whole surface for machining. But mostly the stock material isn't flat to begin with, so I shim the gaps to not bend the part with the clamps. I then cut the various holes and other features into the part, followed by the outer contour to about half the depth. Then I switch to the flattening bit to make the surface flat and also cut away all the burrs from previous operations. And then the program waits for me to switch to screws to finish the outer contour. And like this, I cut all the parts. Some I also just tapped. And of course, I also had to crash into the shim, destroying this brand new bit. At least I can continue, so I removed all the bigger chunks, flush trimmed the edges, and made new grooves for the second side. I then used pins to precisely position the parts for the second side. That works because I have the same hole layout in Fusion 360, so the software position and the real position match, and I don't even have to probe the parts. Most of the second side operations are holes, chamfers and big chamfers, and flattening to thickness. Basically the same for every part. And there are all of them finished.
And none of these parts are sanded, but by using the right techniques and especially order of operations, I get these clean and sharp edges everywhere on both sides. Let's check the fit. Ah, beautiful.
Before assembly, I inserted a few nuts and some steel pieces that I first needed to make. However, straightforward. They will be used later.
I'll do the assembly here on the table saw, because I know this is a flat surface, starting with the back and middle piece. The bottom edge needs to be flush, and then I can transfer the holes.
All these screw joints got a clearance hole using the existing holes as a guide, then a pilot hole, and then a screw. That way the drill bit doesn't wander in the plywood edge.
Then the top plate flush with this edge. the left and right side.
but they needed to be clamped in position.
Lastly, this bottom piece, but it seems to be just a hair too wide. So that's the sled skeleton almost complete, and because of the way I designed this, all the pieces are kind of squaring up each other, making this a square block all around.
With it all together, I could remove a few screws again and replace them with the dowels to make it a more permanent connection. Next came two pieces for the motor mount, except they didn't require the CNC router, and then they got bolted on with the nuts I previously installed. Then I made these angled pieces that close the gaps between the top and back plate and glued them in place. With the glue dry, I flush trimmed all the dowels and then cut a large bevel, which is for clearance when tilting.
That's the finished sled frame. Let's add components to it. The gearbox with belt goes in here, where the housing gets bolted to the bottom, the bearing block to the top, and the motor goes here. Yeah, what motor?
I've prepared something for that.
I picked up this crappy little table saw for free from the garbage, where it belongs. I mean, I'm terrified of this as a table saw. But it has a nice little motor.
I just need to free it from all this terribly dangerous table saw crap.
And there it is, freed from the pile of scrap metal. Nice and quiet, 700 watts and 2800 RPM. That's great. The capacitor and wiring I'll mount elsewhere, so the motor really is as compact as possible. Something strange though is this. A significant rubbing noise coming from the back. So I took off the back cover and couldn't believe it. There are two pieces on the fan that are intentionally rubbing on the housing. Why? Was this supposed to be a motor brake for the table saw? I don't know. Let me know what you think in the comments, but this will go. Even spring-loaded.
Now right here on the shaft needs to be a flat spot for the pulley set screw. I could hold the shaft in place with vice grips and use a similar file contraption as before. Only this time the shaft isn't hardened, so I could use a normal file.
The rest of the shaft is too long and I also don't need it, so off it comes.
I then let it spin to clean the end and chamfer it before I started working on the motor mounting brackets. I cut them from some steel flat stock. Another job for the big ass file, getting the length right until they fit in the sled. Then I transferred hole positions, punched them and drilled them. For the slots, I drilled multiple holes that slightly overlap each other, so I could fit a jigsaw blade to remove material, so I could fit a Dremel to remove material, so I could fit a file to finish the slots. Not my best work, but the slots work and that's what counts. Then I transferred hole positions again, drilled pilot holes and added screws. I couldn't reach the top screws, not even with a driver bit in pliers, so I opened up these holes and used hex head screws. Now that's a solid mount to bolt the motor to.
Well, I've got a problem. I cannot get these back screws installed. There's just so little space, and I knew this would be difficult. I can get them in place, but then just can't get the thread started and the screw jumps around. And the pulley isn't even installed yet. I don't want to drill access holes in the top because I wanted that closed off. Yeah, but I have an idea that might work.
With a threaded piece, I can hold the bolts in the lathe chuck and work on the threads. I had to shorten them a bit and then remove the threads of the first couple millimeters.
So now the screw can fit in the hole and stays in place, making it much simpler getting the thread started.
Then I also realized I could remove the front support for more access.
Nice. And the threads are in. Alright, now I know how I can mount the motor and can continue with making the pulley.
It's relatively simple and starts from this piece of aluminum from before. First facing, turning the major outer diameter and the step to size. Then I again mark the surface to easier locate the edge and the starting depth. and then turned the 3 slots just like before. Here I also broke the sharp edges with a file. And lastly comes the hole. I first removed most of the material with a drill bit, then measured the actual motor shaft and turned the matching bore. Checking with the motor, and that's good. Flipped around, I could part of the rest, or at least that was the plan. Luckily, only a static damage, and I could continue. Everything left is facing to length, turning the second step, deburring the hole, and making the threaded hole for the set screw.
For the wiring, I 3D printed this custom lid. It fits one of these cable clamps. The capacitor has its place here, with the wiring going internal through this hole. And when it's assembled, the hole will line up with this one that I need to open up.
Not only that, but also cutting through the top. Then I finished up the wiring, gave it a test spin, and closed the lid. That turned out nice. Another addition before testing the gearbox with the motor are 2 bearings on top of the gearbox output. They are the axial support and will take load away from the other gearbox bearings. But having just a plain bearings on top didn't work so well and was wearing the surface quickly, so I printed these cover parts from TPU, turned and chamfered them and pressed the bearings into them, like wheels. That's better. And back to the motor. I spent some time installing it back in the sled, got the belt on the pulleys and tensioned it. It's also important for the pulleys to be aligned to each other, which I could adjust and check with a bore gauge.
And now it's ready for the first power test. It works. Woohoo!
What a strangely soothing and satisfying motion.
Very nice so far. Now I will remove everything again, because moving forward it's easier when there are less parts and weight. For the sliding hardware I'll be using a linear rail with 2 blocks, because this set is with just about 40 bucks pretty unbeatable. The blocks have 2 precise surfaces, one where it gets mounted and one here that runs parallel to the rail. And to get them aligned on my sled, I've machined 2 holes for pins where I can slide them against. Mounting them to wood isn't really ideal, but at least I've all the surfaces machined. And here I thought about access holes. That's the sled finished. Next, it again needs to be mounted in something, which I call the carriage.
It basically is another wooden box around the sled where it can slide up and down in. It also holds the mechanism for raising and lowering the sled, and later the components for the tilt feature. Just like before, I prepared all parts for the CNC router and let it do some magic, like this. Or this. How about this? And that. Or this. And then all the other sides, as well as some manual work.
These are all the parts, and the assembly is quite similar to the sled.
All the hexagonal holes receive some nuts. 2 holes get threaded for a screw that will later be an end stop. The smaller parts are bushing and bearing housings, and then there are again alignment pins for the linear rails.
The assembly starts with these 2 alignment angles in the side piece.
And like before, everything gets a pilot hole and a screw.
They are the alignment and square reference for the front. And now this is nice and square. Next is the back. And the other side on top, so I can clamp at the bottom. Then the bottom, which also squares up the back. And finally the second side, which now has lots of alignment surfaces. Alright, that's the carriage assembled, and I now need to check if the sled with rails attached fits inside here. And it fits. Nice.
Just a little bit of friction and it's not getting tighter.
Oh yeah. Seeing this work is so satisfying and quite a relief, because there's already a lot of time invested here.
I slid the rails against the pins and screwed them down.
The 2 rails should now be parallel to each other, but we can also check that.
with a dial indicator mounted on a block.
About 1/10 of a millimeter variation. And against the face, it's a little over 2/10. If I'd be building a CNC router for steel, that would be terrible, but in this application, where also the frame is wood and not that stiff, that's perfectly fine.
And knowing that, I could replace some screws again with dowels, holding it together for good.
While that's drying, I can start working on the assembly that will go here, that interacts with the slot in the gearbox, and also allows the raising and lowering of the whole sled. And when you look at the available space left, this had to be very compact. Conceptually, there needs to be this bearing mounted rigid, so the gearbox can push the sled up and down from it. And additionally, I need to be able to move the bearing up and down.
The very first concept I had in mind, I guess could have worked, but I'm glad I scrapped it for this one. There are some steel parts that I took care of right away. First a pin, so lathe work. Relatively simple part, first facing the end and making the M5 threaded hole with just a little bit of lubrication. Then turning the outside, the overall biggest diameter, then the 12mm part, a bit less for the M12 threads, and then the 8mm section for the bearing. Then adding a lead and chamfer for my tailstock threading die holder I built last year. What a great little tool. And after that I could cut it off. But something seems wrong. This doesn't match the drawing. I forgot to add the thickness of the cutoff tool. Starting over is so much fun. But now I could chuck it the other way to face it to final length and cut the M8 threads. In the vise I filed the wrench flat and this part is complete. Next is a plate for which I could use the offcut from before. I just needed to bring it to length, mark the hole location and drill it. Lastly, another plate that I cut and sanded to size so it fits the cutout in the carriage. For the slot I used a step drill, removed the middle with the jigsaw and filed the rest. Perfect.
Okay, I need one more part from the CNC router to demonstrate the concept, and like the gearbox output, it also has a ramp. This material is not wood, it's called HPL and it's kind of a mixture of wood fibers and resin compressed together and with a pretty hard and durable surface. It's also weather resistant and dimensionally stable, but I can easily machine it with woodworking tools, thus making it a very suitable machine part. This gets bolted together, then in the slot, and the ramp on top, and the bearing. And now as I slide this left to right, the pin slides up and down. All this now just needs proper guides so it's solid and works smoothly.
My material choice are sheets of polyethylene, which are dimensionally stable with low friction. I could use the same hold-on techniques from before and also use my woodworking tools, just a bit less aggressive. Great camera placement. In general, quite an easy material to work with, but the chips can get pretty annoying sometimes.
Now with this cut and still clamped, I can check if the depth of the step is the same as the thickness of the slider. And I can already feel and tell that's not the case.
6.34 for the thickness and 5.98 for the step. Let's fix that.
Ah, that looks good now. And with the lid on top, it can still slide freely with little to no play.
Some more features for the other side and onto the smaller guides, which are basically the same but simpler and with additional manual work.
And there I've got 6 nice parts and one glorious fail. One of the guides for the metal plate was supposed to be aligned square with pins, but something obviously went wrong there and this won't be helpful. However, the hole in the backing plate is accurate, which I can use as a pivot and then align it with a square.
Did I just say one fail? I meant 2.
That's better. Nice and smooth and very little play.
The pin got an acrylic glide bushing, which I machined to a perfect slip fit and reamed the hole. The acrylic is hard, has low friction and had just the right thickness. Then a lock nut to secure, but not tighten it. The other guides received some nuts before the installation.
What? Ah, great. The holes don't line up.
And a drill doesn't fit, so guess who spent some quality time drilling holes by hand? Me having to watch this again is just as painful.
Okay, now the next problem. The slider doesn't fit.
At least that's an easy fix with some precise table saw cuts.
Perfect.
Then just adding the lids and the bearing.
Wow, that took quite a while, but now it works smoothly. The bearing feels solid with little play. That's good. Next is the hand crank coming out the side to control the height.
Which involves all these parts. This 3D print receives some nuts and gets screwed to the slider. This little trapezoidal nut needs to be flat on one side and gets mounted to the slider as well. The little bearing flange from before gets screwed to the outside with the threaded rod right through.
The nut is just a little snug and still moves, which allows me to now align it with the spindle axis and then lock it in that position.
Next I turned a tip to one end, which I could use to transfer the right hole location into the guide rail. It's hard to see on camera, but there needs to be a hole for a tiny brass bushing. So turning some brass to a light press fit and then the hole, which I started with an 6mm end mill and then used another end mill in a bushing, in a bushing, in a mount, in a tool holder as a tiny boring bar, and that worked pretty well. The remaining wall thickness here is just 0.25mm, but it worked.
With everything back together, the threaded rod should now just fit in the bushing. And it does. Nice. This now allows me to pull the slider towards me, and to push it, I have this adjustment ring against the bearing, with access to the screw here. Very nice. And lastly, the hand crank. It's a 3D print and I'll mount it with one of these clamping rings that I drilled 2 threaded holes into. The shaft is still too long, but I'll shorten this later, because now I want to see how and if this works together with the sled.
That's an extremely important test, since the whole sled weighs 10 kilograms. So as an afterthought, and just in case, I'm installing some gas springs.
Alright, and there I should get oscillation. Oh yeah, it works. Okay, and now with gravity on, lifting 10 kilos. It's pretty smooth. Nice. Isn't this amazing? That was without the gas shocks, all the weight just on the gearbox.
So let's hook them in and try again.
Well, I can't tell much of a difference here, but the hand crank. Oh, that's now so easy to crank up. That's without the gas shocks. And that doesn't sound nice. And now, of course, with the motor. Oh yeah. Nice. Now that's a huge milestone, but next this, once again, needs to be mounted in something. And I call that the trunnion assembly.
Yet another wooden box, and it's what allows the tilting motion, and is also the machine base that holds everything together and will later also carry the table and dust collection. The most interesting parts to start with are of course the trunnions, which I again make from polyethylene sheets, but thicker. It wasn't flat to begin with, so I shimmed and flattened it before the actual machining. But then it's not much different from other parts so far. So cutting holes, chamfers, flatten it to thickness, and mount it with screws for the contour. Once done, I checked the trunnion width, and since it came out right, I could already cut away the remaining stuff, position it with pins to remount it, and cut the second side to finish it up. But eventually, the camera was tired. A clever detail is that the holes I used for positioning on the CNC bed are now also used for positioning the part on the carriage. Everything has a purpose. Then just making the second one.
And this one has a little bit of a flexible section. There's this tapered hole where, for example, a screw head can spread this slot open, which then wedges the trunnion in place. The actual piece, of course, won't be a screw head, so let's get that made.
A slightly more interesting lathe part, starting out simple with a threaded hole. Then I turned down the major diameter and the smaller end to finish dimensions, and scribed where the tapered section needs to end. Then I set the compound to 15 degrees and whittled away the material up to the scribe line. Going by eye is accurate enough since I added enough clearance on other parts. And it seems to work, so I smoothed it out a bit, cut it off, and went to the disc sander for the flat. That's necessary to properly start the hole for the pin that gets hammered in place and will prevent the cap from spinning in the hole.
These are done, so next are their matching parts, which are also the machine base sides and the most complex parts to machine.
That's because after machining the first side, I needed to take it back to the bench and glue on this additional part. Well, in terms of complexity, that was mostly the programming. There are just lots of operations on this part.
That was the roughing cycle, where this roughing bit made a super nice job of creating tiny shavings that basically never clog it up. Alright, the machining is done, and if everything went well, this should now not fit in the slot. And it doesn't. I intentionally made this too small at first, so I could now sneak up on a good fit. And a little problem, because I didn't surface at the end, there's a lot of fuss going on, so I run the chamfer bit along these edges to clean that up. And that is pretty nice. And there's the second one. Let's test if that clamping feature actually works. So now it's loose. I give it a little spin. And it does. Oh yeah, that's tight. I have not tested this before. If that wouldn't have worked, I would have been kind of screwed. But I also couldn't think of a way why this shouldn't have worked. But I'm still glad it does. Oh yeah. Ah, that's great. You've probably also spotted these integrated gear teeth, which in combination with a small gear allow me to precisely adjust the angle with a lever.
And in addition to the gears, I also turned some gear mounts, very similar to the pulley support, with a simple reamed hole, 3 threaded holes in the face, and 1 more for the set screw.
But to try all this out with the carriage, I first need to assemble the rest of the base.
And that is the bottom plate and 2 support ribs. They again got nuts inserted and 1 threaded insert where I tried the drill press.
Nice.
And then again, it goes together like a simple puzzle. The 2 ribs go into the bottom plate first, providing alignment and square reference for the sides, which can then be clamped and screwed together. And there's your 5-part 3D puzzle complete. Only thing left now is mounting the trunnions to the carriage with the gears already in place, the 2 bushing blocks inside, and temporarily securing the taper cap.
Alright, and now for the first time I can try to fit the carriage in the base, which I have to do like this. Oh, and it fits. Nice. It's also very smooth. There's also a small air gap here and here, so the carriage doesn't rub on these surfaces and only glides on the plastic. The gears are still free to move, that's good. And the whole carriage by design has about 1 mm side-to-side play for clearance. And when I lock it at some angle, it will always get pulled towards this side, removing the play, while this trunnion then just wedges itself secure. So next, I can get the gears functional.
And that's done with a shaft going all the way through to the other side, tightening the set screws to it, and remove the saddle gear backlash with the bushing blocks.
The handle is similar to before, a clamping ring that I cut threads into, and a 3D print, but this time it's more of a lever type handle because you do less than a full rotation with it. And there it works. Nice. I wasn't sure, but this feels like a good size for my hand, and with the gears I can be super precise with the adjustments. That's nice, but how to lock the angle now? Well, you've maybe seen that this shaft is actually a tube where I can now stick a threaded rod all the way through. The end will find the threads of the tapered cap. You can't see but hear it. When I'm turning left, there the last thread skipped, and now I can thread it in.
Now I just had to bring the parts to the right length, so all this can work. I also reduced the diameter where the set screws mangle up the surface, so the tiny burr doesn't protrude past the main diameter. With 2 nuts, I could tighten the rod into the tapered cap, then the handle with a washer, another washer, and the knob.
So now I can set an angle, give this a few turns, and it's locked on both sides, all done from here. That's what I think is intuitive and easy to use.
Later in the build, I made this even better, because with the weight of all components, setting an angle was getting pretty hard. So I installed 2 gas springs that made a huge improvement.
Much better.
Of course, we also can't forget about an angle gauge and a pointer that mounts to the trunnion with a little stud.
The base as open box with the 2 ribs right now is pretty strong already, but obviously not enough.
So to act on that, I glue together a solid hardwood beam as a structural member, which I then milled square, cut to width, and set up the bevel cuts. This may look a bit sketchy, and I wasn't 100% comfortable with the offcut sliding down the blade, so my dad hit the emergency stop as soon as the cut was done. Then only cutting it to length, which I screwed up and had to go through all this to give it another try. That's more like it. The piece also got some holes for mounting the table, and with some setup work for the counterbores, and a counterboard hole in the middle for the end stop bolt. Yeah, don't ask. I cut a few threads with a tap and forced the bolt through the rest, making it very tight. Now let's mount it.
I transferred the whole location, but will drill the pilot hole with a slight offset so the screw will really pull it in place.
There you can see the offset. With that in place, I can install the 90-degree end stop and the 45-degree end stop, the bolt in the front beam, with both of them now being metal-on-metal contacts.
And there I've got a big structural piece with integrated end stop, and it will also hold the table, which is next. And as you might guess, it also has features and won't just be a simple board.
It's made from multiple pieces, and depending on which sanding drum or belt is used, has different table inserts. First of all, the sub-table that holds everything together. Another CNC routed part, and after the first side is done, I check the groove for the C-channel rail, which needs some adjustment. Difficult to see on camera, but it's a better fit now. Then with the second side done, I can align the C-channel flush, mark the other end, cut it off, and sand it to the line. Would be a perfect job for an edge sander, you know? I also drilled 2 more mounting holes because only 3 seemed not enough. The material below the C-channel got quite thin, so it got a reinforcement piece that also gives the C-channel screws a lot of meat to bite into. The actual table surface plates are made from the same HPL sheet like the slider or gears. That killed yet another bit. God damn it, I was too optimistic again. Let's better go on with some manual work like reaming 2 holes and chamfer the edges. Next, I needed some steel brackets, but the right width was out of stock, so I cut a wider piece in half.
I really don't want to file these to final width, so I have an idea.
The pieces are small enough to put them in a tool holder. I just made sure the tool post is trimmed in square, placed 2 spacers under the part to raise it to the center, clamped it down and just went for it. I mean, the lathe theoretically is a mill. After the first pass, I also added power feed. The results speak for themselves.
Not bad.
The longer piece I could do in 2 setups, and I could also take much deeper cuts. 8mm depth, no problem. With the same setup, I could then also cut the parts to length. Then just marking and drilling the holes, then rounding the corners, and they are done.
They now all fit into pockets on the underside of the table and will later hold the various insert plates of the table. Some of them can also swivel, but it seems like I forgot to cut the pocket for this one here.
But that's no problem. Thanks to the hole grid, I can just remount the part and let the pocket magically appear. The last parts missing are the insert plates, but they're just some more CNC parts, so let's skip that and go on with the assembly. Like before, there are a bunch of places for nuts and bushings. Then I screw on the support beam and drill the holes for mounting the rail. M5 threads right into the wood. If you wonder if that's strong enough, well, it stalls my little drill in first gear, so yes. Now the top plates.
I didn't want any screws through the top to have this nice and clean look, so they're gonna be screwed on from below. There I have all these holes for short M6 bolts, and I'll cut the matching threads right into the tail plate with a bottoming tab. Nice and clean, without any screw heads or holes, except for these two, but you'll see later what they can do.
Next are the steel brackets. The ones that can swivel have a bushing, a brass washer and a spring washer, so they are always tensioned.
Nice and tight movement without play.
However, a little bit of flex, and that's what these slots are for. I marked and drilled a hole in position for another screw that supports the end of the bracket and removes all the flex.
Only problem, these screw heads collide with the slat at 45 degrees, so I have to drill some clearance holes. Except for the inserts, that's the table complete, and I can mount it with 5 bolts. 3 in the front beam and 2 in the back, and some blocks that are screwed and later glued on. Now, when I was about done with the table, the second package from JLC 3DP arrived. Because they not only sent 3D printed parts, but also CNC machined table plates from aluminum that are hard coat anodized. Wow. Everything is cut to spec, the cut and surface quality is beautiful. The threads are already milled in place, that's really nice. And even the slightly complex 3D shaping that's required for when the spindles tilt is there. Very cool.
What an amazing upgrade. Except that the holes in the back are missing, because I added them after the order, so I have to transfer their position and drill them now. With this tabletop, I could now also finish all the inserts and make them a perfect fit. And here's how they work.
First, the insert plate gets screwed to a sub-insert plate to make it stronger, and it also houses 4 leveling screws. 3 different kinds of insert plates. This one is for the biggest drum, this one for all the other sizes, together with smaller inserts for each size, and this one for the belt. For the big drum insert, I need to flip out this metal bracket and this one, so I have 4 positions for the leveling screws. And the weird shape, of course, is for clearance when the spindle is tilted. Then for this insert, I don't need this bracket, but the other one in the corner. And the individual small inserts sit on some more leveling screws just in there. Lastly, the belt insert doesn't need any of the flipping brackets and just sits there in the corner.
But to prevent it from sliding around, it gets a pin that fits a hole in the long bracket.
Oh, perfect. Now I've got all this done, but still can't sand. So it's finally time to make the belt tension assembly and the sanding spindles.
The tensioner has 3 rollers. 2 of them are stationary, which already give me 2 different diameters to sand against. The third one is for belt tensioning. And all controls are tool-free and easy to reach on top. Quite a complex assembly, and the base is again some CNC cut parts.
But I think we are all tired of that, so let's just grab them right from the screen. Ugh, not the belt. Yeah, that one. Very convenient. And I also don't think you need to see me making simple bushings. Much more interesting is the main drum, for which I have an offcut of a huge plastic sheet.
It's gonna be made out of 3 pieces, and since it's plastic, that means a lot of lathe fun. Machining this is just easy. So first I turn the middle piece to length, to a roughly oversized diameter, and then drill and bore a precise hole for the shaft. Well, it sounds kinda wrong, but a slip fit is what I'm looking for. The outer pieces are a bit thinner, so more turning fun. Facing is easy, drilling is easy, and boring a precise fit is also easy. But I still made sure to remove the same amount from both sides, so internal material stress is still evenly distributed. And then I also shaped the ends to dimension. Next I made a template for the whole pattern that once again just fits over the pieces to transfer the positions with a drill. The middle piece then got the M8 threads, and because it's plastic and nothing is sharp, I can do that like this. Never attempt that with aluminum or steel. The outer parts got M8 through holes with counterbores. And another template for the pinholes that match with the drive block.
And now I can assemble the drum on the shaft itself and screw it together.
M8 is definitely overkill, but I already had the bolts, so I used them.
Now I've put another shaft on the lathe to finish the drum on. I'll use one pin resting against the jaw to transfer power, and with the help of a few bellbow washers, the tailstock will support the shaft center and press the drum against the chuck.
Then I could finish turn the biggest outer diameter and turn the channel in between. Here the chips can be really annoying, but at least removing them is quick. Now just touching up this side and it's done.
Now I remove the outer piece again to add the grippy material.
A simple solution would have been heat shrink tubing, but it being relatively thin, I didn't have too much trust in it. So I printed these thicker rings from flexible material that get stretched over the cylinder, which then gets bolted back together, and I can turn the flexible rings to final diameter. Really funny shavings. Could also be my back hair. Wait, what? My target was 75.6. Close enough.
It's not as